So here is another integral for you to practice, and it's an indefinite integral, no limits, and it is an exponential of the square root of x. And if you give it a go with pen and paper, the solution and some comments are on the next slides. If you wish to have a hint, I will just give you the hint, and if you don't want to have it, just press stop and have a go first. Okay, my hint is this is a two-step integral. You've got to do two things, one after the other. Okay, so now let's pause and you can come back after you've had a go at it. Welcome back. Let's have a look at the answer on the next slide. So, in this integral, I would expect that you will have noticed that the exponential in the argument has as its argument the square root of x, and that is the key thing we need to notice. So we have a function of a function, and that will make us think about integration by substitution. Now, my favourite form of integration by substitution is integration by inspection, but I really don't think this is easy to write down by inspection. So instead, we're going to work through it more methodically. We're going to try the substitution. U is the square root of x, so u is a function of x, and we're going to recall the substitution formula, and I think it's very helpful in such cases to write the formula out explicitly. So what it says is if you are integrating a function of our variable, and this function is multiplied by the derivative of this function with respect to x, and then you integrate with respect to x, then this is equivalent to the integral of the outer function f of u with respect to u, and at the end you can replace u by u of x. So, in our case, u of x is the square root of x. Du dx is a half 1 over the square root of x. Square root of x is x to the half, the derivative is a half, and then x to the minus a half, which means 1 over the square root of x. So we'd like to have this factor in our integrand, but we don't have it there. But what we can do is we can insert a factor of 1, and 1 can be this factor, the du dx that we need, multiplied by its reciprocal. So our integral is the integral of 2 times the square root of x, this factor, times the e to the x that was already there, multiplied by 1 over 2 times the square root of x in the denominator here. And when we look at this, this is the du dx factor that we need for a substitution, and this is our new integrand. This is what is called f of u of x in the formula. So this idea of inserting a 1 is sometimes very useful. And if this factor is already there explicitly, then I wouldn't normally bother doing all of this. I would just try to see if I could do it by inspection. Okay, so we've inserted a factor of 1, and this is our new function. And the reason why we should now be very happy is that this function can be written very easily in terms of u, because the square root of x here is u of x, and then we have e to the u. So from this formula, our integral is equal to, well, there's a factor of 2 here. I'm going to pull it outside of the integral just to make it look a little bit less intimidating. And then it's the integral of, now, root x is u, e to the root x is e to the u, and this product here, du dx dx, can be replaced by du. So this is now the integral that we need to calculate, and if we look at that, I hope we'll agree that this is a doable integral, but it needs the use of integration by parts. So I'm just going to go through that on the next slide. So again, just to cover this again very briefly, we looked at this, we saw this was the problem. we couldn't see that this was easy to integrate. If there had been, for example, a 1 over square root of x outside, we could have done it by inspection. So we have to use this key formula. We write it out explicitly, and we don't have this here, but you can always try to insert a factor of 1 of this multiplied by its reciprocal and see if this gives you an integral you can do. And in this problem, it does give us an integral we can do, and we're going to finish it now. So, on the previous slide, we saw that we were able to rewrite this integral as 2 times this integral where u is the square root of x. And we're now going to calculate this integral. Now, because I've chosen to call the variable u, when I use integration by parts, which I'm going to do because this is a product, and the product here, I can't do it by inspection, but I see that if I were to differentiate that, it would just give me a 1, so parts is likely to work. So I look at this and I think, okay, here's the parts formula, and sometimes people write it as u and v. I'm choosing here to write it as f and g. The reason being that my variable is u and I don't want to confuse myself more than necessary. So this is our formula, and we have to choose in this product here one factor to be differentiated, f goes to the derivative of f, and one factor to be integrated. And I think it's clear that we'd be better off choosing to differentiate the u because it's going to go to 1, and whether or not you integrate or differentiate e to the u, you're just going to get e to the u. So f of u is u, the derivative is 1, g dash of u, the other factor here, is e to the u, and the integral of e to the u is e to the u. So from the parts formula, our integral is equal to, so it's 2, which is going to multiply everything. So 2 multiplies everything, so I'm going to open the big brackets afterwards because it's going to multiply both of the terms here. So it's f times g, f is here, g is here, u times e to the u, minus our new integral, hopefully it's becoming simpler, and this is integral of f dash, which is 1, times g, which is e to the u. So this is just e to the u. So it's now become a standard integral. So this is now 2 times, remember 2 is multiplying everything, u times e to the u minus, and this integral is just e to the u. And now we've calculated the integral. There was hidden in it an uncertainty and ambiguity due to an integration constant. After we've calculated it, I'm putting the integration constant explicitly at the end. So this is our answer for the integral, but we should remember that u is the square root of x, so we can rewrite our result for this integral as 2 times, and now e to the u is a common factor. I'm going to pull it outside of these brackets. E to the u is e to the root x, and here we've got left u minus 1. So it's root x minus 1, and this is our result. And a really good habit to have is to check this by differentiating our answer and seeing if it gets back to this. So what we're doing by doing this is we're also becoming very good at differentiation. So we're going to differentiate this. We're going to need, therefore, the product rule. And the way that I would always write out the product rule is if we're differentiating two functions, and let me say that they are u and v, it doesn't matter what they are, it's going to be the derivative of u times v plus u times the derivative of v. And this lets itself generalize very easily to products of multiple functions. And it's also very systematic doing it this way. You differentiate the first factor, multiply it by the second, and then you add the first factor times the derivative of the second factor. So 2 is a common factor, it's just a number. I can pull it through and leave it there. Open a big bracket, 2 multiplies everything. And now we're going to differentiate this bracket and multiply it by e to the root x. The derivative of this is 1 over 2 root x, so it's a half, and then it's x to the minus a half, so it's 1 over 2 root x. So that's the first term in the product rule. And then we add, and then the second term is going to be this factor, so that's the u here, and that's not differentiated, times the derivative of e to the root x. And now, the derivative of e to the root x, we've got to use the chain rule. So it's e to the root x times the derivative of the argument root x. And now we use the chain rule to work this out. So it's going to give us a half 1 over root x, this factor again. So we have, and I'm going to pull out the e to the root x that's everywhere as a common factor. So we've got the 2 at the front, we've got 1 over 2 root x from here, and then we've got plus root x minus 1 times 1 over 2 root x from here, all multiplied by e to the root x. And now I just want to expand these brackets and multiply this out. So we get, there's a 2, by the way, in the front, and there's a half multiplying every term. So I'm going to cancel the 2 and the half. And here we're left with a 1 over root x. And then here there's a root x divided by root x, so that's plus 1. And then there's a minus 1 over root x. So this term and this term are going to cancel. And we're left with 1 times e to the root x. And that is exactly the integrand. So what we've done is we've differentiated our result for the integral, and we have regained the integrand, and we have that happy feeling of knowing that we've got the integral right. So the method we've used here today is very useful, and it's not always guaranteed to work. This was deliberately chosen to be an integral where it would work. And tomorrow we're going to discuss some examples that are a little bit more general.